Hello students, welcome back. In the previous video, we talked about the Cartesian product and relation and went through some examples and the domain and range of relations, and then went through some examples. All right, let's begin defining a function. A function is a special relation where each x in the domain is related to one and only one y in the range. Here's an example. Each married person must have one and only one spouse. If not, well, this relation is really dysfunctional. Here are three ways to represent functions symbolically: pair notation, arrow notation, and algebraic notation. Among these three, the algebraic notation is going to be most useful and we're going to use it most often, but arrow notation will be used very often too. Now the pair notation, we're never going to use it except today. But today we have to use it because that one is directly related to the definition of the function, directly related to the concept of relation. So this is hard, but we're going to go over that just once in a lifetime experience. If you're not really understanding it, try to get as much as possible and just move on. If you have difficulty understanding B and C, now you have a problem, but A is not going to kill you. Okay, let's come back here. Let capital F be a function. That means it's a relation. It's a subset of the Cartesian product and non-empty, of course. Now, F is a function if each x in the domain belongs to, each x in the domain is related to one and only one y value. And how do you write it? X comma y1 belong to this function, and x comma y2 belong to this function, then y1 and y2 are the same. That's a little bit formal way, but that's really vigorous way, but it's a formal way to write down that each x in a domain is related to one and only one y value in the range. For example, this course, Math 1324, is taught by Dr. Kang. This code is taught by Dr. Ike. But then again, Dr. Kang and Dr. Ike are the same. It's me. See what I'm talking about? X is related to this, X is related to that, and this and that must be the same. That's the same as X is related to one and only one Y. Here's some examples. I got these from the textbook. So here are some menu boards. Dark roast $1, light roast $1, coffee mocha $3, cappuccino $3. Now cheese melt $1, nacho supreme $2, bacon double $3, happy meal $5. Salad oil change $30, high mileage oil change $40, full synthetic $50, full synthetic $60. Now which is not a function? Well, each menu has a price tag, but unique price tag. So it's okay, it's a function. Each menu item has one price tag, so it's a function. Also, this is one-to-one function, by the way, because here more than one menu item share the same price tag, but not here. Now this one, this is problematic. Full synthetic is $50 or it's $60. It's ambiguous. This is not a function. Something is wrong. Somebody made a mistake. With coupon $50, without coupon $60. If so, then full synthetic with coupon, full synthetic without coupon, those kind of things should have been specified so that we have two different x-coordinate values. But same x values assigned to two different y values, this is not a function. Okay, next, arrow notation. So D is a domain, and capital F is sending the domain into a target Y. Elements of the domain X is sent to a certain element of target Y. With set, we use usual arrow. With element, we use this arrow with bar. And then this is a special condition. X goes to Y1 and X goes to Y2, then Y1 and Y2 are the same. Again, same idea. This course, Math 1324, is taught by Dr. Ike. This course is taught by Dr. Kang. Dr. Ike and Dr. Kang are actually the same person, so it's okay, no problem there. There's no ambiguity. Here's an example. Is this a function? Cheeseburger, $1, McChicken, $1, and so on and so forth. Now, second, is this a function? Yes, it is. By the way, this is one-to-one function. We have one-to-one correspondence coming back here. More than one menu items share the same price tag. So it's not one-to-one, but it's a function nonetheless. Now this one, this is not a function. This 240 goes to 12 or 20, which is it? Impossible to define, so it's not a function. Third, algebraic notation, y equals to f of x, where f is typically some algebraic expression. In that case, y is determined uniquely through this algebraic computation, so we get the function notation. Let's see, do we have an example? Oh, never mind. I'm not going to talk about the example just yet. I'm simply saying that these three examples, these three concepts, or these three notation mean the same thing. xy belongs to capital F. Capital F is sending x to y, or y equals to capital F of x. Oh, by the way, one more thing before moving on. This thing here, this one is typically called the value of a function, or the function value. And here's some examples associated with the value of a function. Let's suppose we have a function defined like this as an algebraic equation. So if I plug in x value, then you can calculate this and unique function value comes out. So it's a well-defined function. And then evaluate following quantities. Well, what is f of 3? Do your computation. What is f of -1? Do your computation. And you can do this kind of thing too. Let's see. Shall we do this? Plug in x equal to 3 right here. And also right there. And doing your computation. Make sense? Here, x, in place of all those x, I'm plugging in 3. So plug in 3, and plug in 3, everything else stay the same. And then do your computation, you end up with 9. Same for -1. Plug in -1, plug in -1, do your computation, it's 5. You see, x. You want to plug in x equal to 3, so 3 goes here. Plug in x equal to -1, so -1 goes here and there. Simple? Should be simple by now. Now, what if you want to calculate this? F of 3 minus f of -1 over 3 minus of -1. No sweat. This minus that 9 minus 5 divided by 3 minus of -1, so 4 over 4 is 1. This quantity, by the way, is called the average rate of change, and it's going to be important in calculus. Some more. What is f of -x and negative of f of x? Same deal. We are plugging -x in place of this. So you have to put -x here, -x there. See? -x goes in place of x, and then you're doing your algebraic computation. negative squared, so this becomes positive. Now here, negative, negative, so it's positive. What about this? Negative of f of x, that's different. F of x is this entire thing, and then putting a negative, we get a different quantity. F of negative x and negative of f of x are not always the same. Finally, this quantity, difference quotient or Newton quotient. Yeah, okay, let's. Okay, all right. A little bit difficult to understand maybe, but let's try anyway. Plug in x plus h in place of x here and also there, and that gives me the first term. And then the next, we have just f of x, so nothing fancy, this entire thing. That's how you get the numerator. But then again, we have to do some simplification. So let's FOIL this one out. And by complete square, we get that, x squared plus 2hx plus h squared. And then break up this next parentheses. And then minus of all that, so distribute minus. So we have all the sign change. Let's break up all the parentheses completely. Distribute 2 around. That's the numerator. Now, do you see some simplification? If you did your computation correctly, you will see some simplification. This negative 3x and this positive 3x. And then this 2x squared, this negative 2x squared. And what's left is, as you can see over here, make sense? And then factor h out. And then cancel out the denominator. Bingo, we have this expression, 4x plus 2h minus 3. This kind of computation is important in calculus. Therefore, some instructors really emphasize these. Me, I'm not one of them, but our textbook author apparently is. Okay, so much for value of functions. Do you have enough time? No. Let's not consider domains of functions. Algebra of functions, again, not enough time. So let's stop here and let's resume section 1 in a separate video.